When we talk about strong and weak acids, we're talking about how much the acid dissociates in water. Now, in water, all strong acids are equal because they dissociate 100%. But when it comes to weak acids, they partially ionize. So some of them, though, will ionize or dissociate more than others. So one way we can distinguish between the strengths of the weak acids is by using something called an acid dissociation constant. And an acid dissociation constant really is like an equilibrium constant, like we talked about in a previous chapter, an equilibrium constant for an acid. So the acid dissociation constant is given this symbol K, like an equilibrium constant with a lowercase a. And this is a general formula for what it is. Remember the brackets, like this, those mean concentration. So it's the concentration of the hydronium ion times the concentration of whatever conjugate base it is, divided by the concentration of the acid. Now in this introductory class, we're getting this conceptually more than trying to do calculations. But if you recall, basically in an equilibrium constant, it was the concentration of the products divided by the concentration of the reactants. So what happens is the more an acid dissociates, the more products it makes, and the larger the Ka value is. So here in purple, we get the big takeaway from the conceptual part of acid dissociation constants. And that is for the weak acids, the stronger the acid will be, the larger its Ka value is. So again, this is for weak acids. Strong acids don't have the acid dissociation constant because they dissociate 100%. It's like they're all on equal playing fields. But weak acids have varying dissociation, and so they have different strengths. It's kind of funny to think about a strong, weak acids, but the more an acid dissociates, the stronger it is. So here's a table from your textbook of some common weak acids, and you can see here the arrow indicates that the top of the table would be the strongest, the increasing acidity. And if we look here, look at the Ka values, the top one shown is 10 to the negative 2, and down here in this example, it's 10 to the negative 13. So this is a larger Ka, which then would tell us it's a stronger acid. Okay, and then this one down here would be the opposite. It has a smaller Ka down here at the bottom. So this is a weaker of the weak acids. So let's see how we can relate this to things that we've already talked about. So here's a question. It says, consider the weak acids NH4 plus and HF. So I'm going to have to go back and forth because I couldn't fit that table on both. So I'm going to write both of these, and let's go back to the table. So NH4 plus is right here. So 5.6 times 10 to the negative 10. That's its Ka value. And then let's find HF. HF is right here. We don't memorize Ka values for our point. 7.2 times 10 to the negative 4. 7.2 times 10 to the negative 4. That's its Ka. So the first question says, which acid has the larger Ka? So looking at these two answers, HF has the larger Ka. Remember, with negative exponents, the smaller the exponent, actually, the larger the number. So HF would be that answer. So which acid is stronger? Okay, so by definition, the larger Ka is the stronger acid. And I'm just going to write that next here. Larger Ka equals stronger acid. Then it says, which acid has the stronger conjugate base? Now let's recall, and you can go back and look at the video, but the relationship between the strength of an acid and its conjugate base is an inverse relationship, which means they are the opposite of, whoops, if I can, you guys know I'm not a good speller, relationship, there we go. An inverse relationship. So a stronger conjugate base, inverse means the opposite, comes from the weaker acid. Now if you're reasoning with me, then the weaker acid has the smaller Ka. So if we look back up, the smaller Ka is NH4, so the answer here is NH4+. And I will circle that. I probably should have written it in a different color. This is the answer here. Just so that we know, but that's just the thought process, right? That's how we think about it. A stronger conjugate base would come from a weaker acid, and because there's an inverse relationship, and with the information we know, weaker acids have smaller Ka values. Okay, so that's your thought process. Then letter D said, when each acid is dissolved in water, for which acid does the equilibrium lie further to the right? Okay, so I see this further to the right, and I'm thinking, okay, so the right side of a chemical reaction is the products, right? The left side is the reactant, the right side is the products. So this question is saying, which one makes the most products? Well, we know that stronger acids dissociate more. That means they make more products. So what I'm looking for is the stronger of the acids, and we already decided that HF is the stronger. So being a stronger acid, HF would make more products, and another way to say that is that it would have an equilibrium that lied further to the left.